What I would like to talk about today is to show you that for closed shells, you see the total angular momentum is 0. Okay, now I would like to show this to you. This is a very interesting application also, and this basically, you see, simplifies our life, and we are able to do shell model calculations very nicely because of this. Okay, so let's start. Now let us consider our 18 oxygen nucleus. So this has basically, you can think of it as we have a 16 oxygen core plus 2 neutrons, right? Now let me first talk about protons. Okay, so let us consider protons only in this 18 oxygen core. So if I write down the very shells, then it will be like this: 1s half, then 1p 3 half, 1p half, then slowly 1d 5 half, 2s half, 1d 3 half, so on. Now let us put in the protons starting from the lowest shell. So we have got how many protons? 8 protons, right? So 1, 2, then 3, 4, 5, 6, and then 7, 8. So you see they form the closed core here, right? So if we write down, so this is basically your level, and if we write down the total number of states, so what is this? Basically 2j plus 1. So how many states were there? 2, 4, again 2, 6, 2, 4. Okay, and what is the projection? That is m. So the projection will be plus half, minus half here. What about these 4 states? It will be plus 3 by 2, plus half, minus 3 by 2. Fine. And what about them here? Again plus half, minus half. Okay, so on and so forth. It will be there. Now let me write down the total angular momentum. We know this relation, right? J square is equal to jx square plus jy square plus jz square. That is, we can write j square as half of jx plus I jy into jx minus I jy. This is just basic quantum mechanics I am doing, plus half of again jx minus I jy into jx plus I jy, and with the addition of jz square. I can write it like this. So this means I can write basically j square is equal to half of j plus operator, j minus operator. So this is my idea. I wanted to write like this, plus j z square. So what is the use? Now let us consider each of the 1p half, 1p3 half and 1s half levels. Now you see, in each of the levels, this j plus j minus and j minus j plus levels give 0 value. How? Since you see, by rearranging the particles in each of the levels, their m value cannot be changed by plus minus 1. You see, their m values cannot be changed. Also, this jz square acting on a state never changes its m value. Thus, what we can say is that for closed cores, so we can say for closed shells, the angular momentum is 0 and only the valency shell is to be considered. বোঝা গেছে এই জিনিসটা আমি যেটা বললাম? Again, let me repeat. You see, in each of these levels, this value of j plus j minus and j minus j plus, they give 0 values. Since by rearranging the particles in each of the levels, here, 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 the m value cannot be changed by plus minus 1. Also, the jz square acting on a state never changes the m value. Okay? And as a result, we get the fact that for closed shells, the m value, the total angular momentum is 0. Now, let us consider neutrons. Consider neutrons. Okay, so you see, what will happen? The same thing will happen. For neutrons, we also have 1s half, then 1p3 half, followed by 1p half. Okay, and again they will be filled. They will be all so closed again. You see, the situation is very similar to this one here, which was also closed. However, note the difference. The difference is that here in 1d5 half, only 2 of the protons will be there. Again, here we have 2s half, and here 1d3 half. Okay, now this is the level, and what about 2j plus 1? So this is, here it is again 2, this is 6, 2, 4, 2, so on, and the projections we have also discussed. Now here you see also the same thing happens. That means they form a closed core, 1s half, 1p3 half and 1p half. But there are 2 valency neutrons here. They are the valency neutrons. And this is the valency shell. One d5 half. Now this level gives non-zero value of j plus j square operator. You see? Understand? So they basically contribute to the j square. Fine. Now we have to consider the coupling between the 2 neutrons in this j is equal to 5 half state. So let us do this coupling. Now this technique is known as M scheme. Okay, so what we do here, so we are considering 2 neutrons in j is equal to 5 half state here. d 5 half. So J is equal to 5 half. We are considering 2 neutrons, right? So basically what is the M scheme will tell us what, as a result of these 2 neutrons in J 5 half, what is the value of possible total momentum. This is what M scheme will tell us. So let's see how it is done. So let's start with, I will write down the M1, M2 and correspondingly M1 plus M2 is equal to total M value. So M1 is for one neutron, M2 is for another neutron. Now if one neutron has a value of 5 by 2, by Pauli's exclusion principle, the other neutron cannot have a value of 5 by 2. So what is the other value it can have? It can have 3 by 2, it can have half, same 5 by 2. It can have minus half, again for 5 by 2. It can have minus 3 half, and you see it can also have minus 5 by 2 for the same value of M1 is equal to 5 half. And this gives me total value of M equal to 4, 3, you see the sum, 2, here 1 and here 0. Now these are basically your projections, right? And so they correspond to J is equal to 4. You see, J is the maximum projection of M, right? Similarly, next we can have 3 by 2 here. Then we will not have the value of 3 by 2 here, but instead we will have half. Next we will have minus half. Next we will have minus 3 by 2. And this will give me here the values 2, 1, 0. So this corresponds to J is equal to, J is equal to how much? 0, 1, 2. When can we have that? The projections of M is equal to 0, 1, 2. It can be only possible when J is equal to 2. The other possibility which is left is plus half, and in this case we will have just minus half. And you see, in this case we have just total M equal to 0, and when total M is just equal to 0, one value, then this corresponds to only J is equal to 2. Now I have not considered the negative values here, because they will similarly give me the negative values, or basically correspond again to the value of J is equal to 4. So in a way what we have seen here is that two neutrons in J is equal to 5 half, as a result of their coupling, only J is equal to 0, 2, 4 are the possibilities. They are the only possible states, right? And remember that we have obtained these calculations from following the Pauli's exclusion principle. Okay. And again, Pauli's exclusion principle guarantees antisymmetric states for two fermions, right? Neutrons are fermions. Thus, it follows that J is equal to 0, 2, 4 states. They are, so from these two things, it follows that this J is equal to 0, 2, 4. These states are antisymmetric. Okay. In fact, we can generally say, I will just show you today, that J must be even for two neutrons or protons in the same J state. So, what is the result? The result is that we get the idea that for 18 oxygen, we can have these 3 spins, 0, 2 and 4. Okay, as a result of the two valency nucleons in this shell. And what? There is no interaction, nothing. there is no residual interaction. We are just considering the single particle shell model. So they will be sort of what? Think about it, what they will be. Similarly, I would like you to do this homework of 2 protons in J is equal to say 7/2. Similarly, 2 neutrons in J is equal to 11/2. What if I tell you about 1 proton and 1 neutron in J is equal to 9/2? Can you do this using the M scheme? Remember, this time you do not need to follow the Pauli's exclusion principle stuff. Why? Because we have different fermions. But still, try to do this using the M scheme. What do you think? Will you be able to do this or not? Think about it and tell me in the next class. Okay? Okay. So, with this very basic discussion, let us now consider the... So, we are now moving on to the next topic. So, we will try to consider the spin and parity of the ground and low-lying states of doubly magic plus minus 1 nuclei. So this is the next topic. Now what is a doubly magic nuclei or doubly closed shell nucleus? Doubly magic nucleus is basically, this is a nucleus where both proton and neutron numbers are magic numbers. Or also sometimes we call this doubly closed shell nucleus, DCSN. Examples, very good examples are 16 oxygen and 208 lead, 82 and 126. Okay. Now you see, one can predict the spin and parity of the ground state of nuclei whose proton or neutron number is smaller or larger than that of DCSN. So DCSN nucleus plus minus 1 proton or plus minus 1 neutron, it is possible to predict the spin parity of the ground state of this nucleus. Now you see, to some extent we can also explain the spin parity of low-lying states as well. Let me show you an example. But before that, this is the entire. So basically independent particle model, right? So here what you can see are basically the nucleon energy levels for several spherical mean fields. Now here you see we started with this harmonic oscillator. Remember we did the calculation for that. And this ISQ, it stands for basically infinite square wave potential. I told you the results still don't reproduce the magic numbers. These are the magic numbers. And this WS stands for Wood section potential. You see, only when we include the spin orbit interaction with somewhat modification so that we can experimentally explain the magic numbers, then only we will be able to get this exact shell states in this way, and this will reproduce the magic numbers. So you see the last column represents the energy levels here, this one, where the spin orbit interaction is taken into account. Now we have discussed this in our last. This 208 lead, we just talked about it. So in this 208 lead, where will be the proton and neutron levels filled up to? You see, this 208 lead, it has got 82 protons. So 82 is filled up to this here, okay? So 82 protons are just filled in the states from 1s half to 3s half, okay, up to here. And the 120x neutrons, the 126 neutrons, they occupy all the states from 1s half to, you see, 1f5 half. Now let us call this part, which corresponds to the doubly magic numbers, the core part. Then one can fill the last 127th neutron, called the valency neutron. Suppose I want to see where the 127th neutron in the nearby nucleus, which has got one more neutron than the 208 lead is, where will it be? I want to see. So you see the 127th neutron, which is the valency neutron, it will go to this level, 2g9 half. Now since there is only one way to fill now, so we have basically got the core part over here and the valency part. And what will be the spin parity due to the core part? 0 plus. Remember, we just showed you, right? And as a result, the spin parity of this entire, so 208 lead is our core, right? It is indeed experimentally observed the spin parity is 0 plus. So 208 lead plus 1 neutron, in this case basically I will think of it as the 208 lead core. So this is our core, and this corresponds to J is equal to 0 plus. And this last neutron, where does it go? It goes to the J is equal to 9 half level. Now if you couple 0 plus 9 half, you just get 9 half. Understand? So you see, this is how we can determine the spin parity of the whole nucleus is determined by those of the valency neutron. Hence, the spin and parity of the ground state of this, what nucleus is this? This is 209 lead. Is basically expected to be 9 by 2 plus. Okay, any questions? Okay, so you understand this is it's very basic. Now here in this figure, the left side shows you the spectrum of the 209 lead. Now you see, the spin and parity of the ground state is how much? 9 by 2 plus. So it does agree with the prediction of the shell model that we have just described. Now one can keep the core part as it is. So 209 lead means basically I have this core of 208 lead, right, plus 1 neutron over here, right. Now we can keep this core part as it is, saying that it is unexcited, it's still as it is. And then what we can see is that we can, let us try to change the level to fill the valency neutron from the 2g9 half to another state. So where that state will it be? You see, 2g9 half. After that, where can the neutron go? It can go to I11 half, right? So what I am saying is that we are trying to keep the core part as it is and change the level to fill the valency neutron from 2g9 half to another state successfully from the low energy level in order to predict the spin and parity. Or as an alternative, we can consider the state where the core is polarized. That means it's not J is equal to 0 anymore. And the nucleon in the energy level in the core, it also takes part in the angular momentum. বুঝতে পারছো? এর মানে দেখো এখানে ফার্স্ট এক্সাইটেড স্টেটটা কি হচ্ছে? What is it? 11.5. How do you get this 11.5? You see, only if the core remains as it is, core is not polarized, core is not excited, and this neutron in G9.5, it goes to I11.5, then I can explain the first excited state. So 11.5. But look at the second excited state. What it is? 9/2 plus. Now how can you explain this 9/2 plus? You see, if you just assume that the core is as it is and the neutron just jumps to higher and higher level, then you see, instead of this 11.5, the next level which the neutron will go is 3d 5/2. So the spin should be 5/2. But the spin here you see is 9/2. বুঝতে পারছো? So what I am saying is that this I can explain these two levels, explain assuming unexcited core, or okay, but this level, from this level onwards, core must be excited to explain this. This is what I am saying. Okay, now suppose the core is excited, okay, or polarized, we say, and the nucleon in the energy level, let me write it down, NH, LH corresponding to JH in the core, here where the core is polarized and the nucleon just a second, core is polarized and the nucleon is in this level, দাঁড়াও, energy level, দাঁড়াও, this is in the core, okay, and here H, what does this H? H stands for hole, okay. Now this nucleon is basically promoted to level NP, LP corresponding to JP outside the core. এর মানেটা কি হচ্ছে? এর মানেটা হচ্ছে এই যে কোর ছিল 208 লেডের, it has got sets of states, so one nucleon outside, it goes in the valency shell. So this is what I am saying, one nucleon is going outside the core in the valency shell, but this P stands for particle. Now if the original valency nucleon, it was already some valency nucleon was there, remember 209 lead, so one was already there. So if the original valency nucleon in the NLJ state, then the corresponding wave function can be, we have to write it using antisymmetry, both of them, and the angular momentum will be the result of the two of them. And as a result, what we get here, but remember, since one particle is over here, there is a hole as well left over here. So this state is known as 2p1h state, or basically two particle one hole state. বোঝা যাচ্ছে? And you see, we write down the wave function of this state as a wave function টা এইভাবে লেখা হয়. You see, NH, LH, JH. Since this is a hole, we write it as this, and this is just coupling. NP, LP, JP. It is coupled to NLJ in J prime state. So this is basically the coupling. Although you see, there are many possibilities depending on the way to make a hole. The choice of the particle state to promote the original core nucleon and the way to couple the angular momentum. It depends. Okay? দেখো এখানে কি হচ্ছে, আমি এই জিনিসটা তোমাদের বোঝালাম যে আমাকে এখানে কোর এক্সাইটেশনই হতে হবে, আদারওয়াইজ আই ক্যান নট এক্সপ্লেন দ্য 9/2 level, right? Now you tell me, how can you explain this 9/2 level? How can you explain this using this very basic ideas? You see, you should work this out yourself, how you can explain this thing, but also you should remember that it is also possible that sometimes instead of just one particle over here, what can happen is that from the core one particular pair goes out over here and it can couple with the existing nucleon state. So suppose in this case, so here suppose 127 goes to G9/2, say for example G9/2, then it is possible that this G9/2 state, one pair is excited, and now you know this pair, what are the possible angular momentum they can have? They can have 0, they can have 2, they can have 4. Now, so we can have coupling with each of them. And as a result, we will get 3 possible states. You see, this is also possible. And these all will be there in the low excited spectrum. This I will discuss in more details when I discuss the extended shell model spectroscopy. Extended shell model. So what I was saying is that although there are many possibilities depending on the way to make a hole, the choice of the particle state to promote the original core nucleon and the way to couple the angular momentum, the state where the core neutron is promoted to the same level as that of the valency neutron, and where the total angular momentum of the two valency neutrons J prime, it couples to 0, appears at low energy because of the pairing interaction between the valency nucleons. So in this case, the spin and parity of the whole nucleus must become identical to those of the whole states. Okay, so we have just discussed this, and anyway I was just saying that so the spin and parity of whole nucleus become identical to that of whole state. That means JH and minus 1 to the power LH. Now you see, another interesting possibility is that here you see is that a series of characteristic states appear in the low energy region by the process that the core part makes a low energy collective excitation. This, just as I was telling you, this collective excitation, this one. Okay. Now, as an example, so I have just told you this, so let me give you an example. So here I have shown you the 209 bismuth on this right hand side. You see the ground state and the first state through the third excited states. So ground and the first to third excited states, first, second, third, they can be understood as single particle states, or they can be understood as single particle states, or basically 2p1h state initial model. Now the other states, these are 1, 2, 3, 4, 5, 6, these states here. Over here, starting from this 3/2 to this 5/2 over here, you see, here you can explain this only when the core of can be explained when the core of 209 bismuth, it makes a vibrational excitation of octopole type. I'm not giving you the details yet. I'm just telling you what are the very possibilities. So this is core excitation. Okay. And weakly couples, not only does it do a vibrational excitation, but also it weakly couples with the valency proton in the H9/2 and plus coupling, weak coupling with H9/2 proton. So this is how you can explain this. Now what about the case of odd nucleus in which both proton and neutron numbers are odd? So what about odd nucleus? Now you see, for the case of odd nucleus where both proton and neutrons are odd number, the spin and parity of the ground state and low-lying excited state are expected to be given by what? Minus 1 to the power LP plus LH, and one of the values between JP minus JN and JP plus JN, where this LP, JP and Ln Jn are orbital and total angular momentum of the orbits at the last proton and neutron. Let us take an example, say 14 nitrogen, 7. Here LP is equal to Ln is equal to 1 and Jp is equal to Jn is equal to half. And you see the experimental data for spin and parity of the ground state. What does it show? It basically indeed show 1 plus. Okay. Okay, so as you have requested also, let me just write it down, this core polarization part for you in details. So I was saying is that we can keep the core part. So core part intact, and this is regarding the discussion, right, for 209 lead. I can keep the core part intact and change the level to fill valency neutron, right? এই পার্টটা তো তোমরা বুঝেছিলে। We can change the level to fill the valency neutron from 2g9 to another state, right? Now our alternative হচ্ছে, what's the alternative? The alternative is we can consider the state where core is polarized and the nucleon in energy level NH, LH corresponding to JH in core, it is promoted outside to level, what's the level? NP, LP, JP, outside the core, right? Now already we have original valency neutron in the level NLJ state, right? So what will happen? এদের দুজনের ভেতরে coupling হবে. So we can write the wave function as NH, LH, JH. This corresponds to hole, so that's why it is like this: NP, LP, JP again, and here NLJ. You see, this is coupling to J prime. And this is how you write the wave function. Now you see the state of this kind, this configuration is known as 2p1h or 2 particle 1 hole state. Although there are many possibilities depending on the way to make a hole, the choice of particle state to promote the original core nucleon and the way to couple the angular momenta where core neutron is promoted to same level as valency neutron and where total angular momenta of two valency neutrons J prime coupled to 0, this appear at low energy because of the pairing interaction between valency nucleons. Okay, এর জন্য যেটা হয় যে total spin and parity of whole nucleus becomes identical to that of whole state, and we can write just JH and minus 1 to the power LH. This is what I wanted to say. Acha, already I have discussed how you can think of the total core having in the total J is equal to 0, J pi is equal to 0 for the core, and also not using wave function but rather using the M scheme. I have showed how the coupling between two identical neutrons or protons in a state, it gives you even values of J. Right? I'm not showing you the entire wave function argument. It is little bit harder, but talk about a different important part which I talked about little bit qualitative in my last class, and this is basically the effect of delta type residual interaction. So residual interaction now we are slowly going to incorporate. So the first is, let's incorporate a delta type residual interaction, and this is basically pairing correlation. Okay, now you see the shell model which assumes that nucleons move independently from each other in the mean field under the constraint of Pauli's exclusion principle. It very well explains the basic features of nuclei such as shell model, independent particle model. It very well explains your magic numbers. However, it has to be refined by taking into account by effects of residual interaction in order to explain the finer details. Which appear in experimental data. Okay. Now this is very important. So now I am not going to write the entire Schrodinger equation, but I am going to write it in a little bit short. So let us rewrite the Schrodinger equation again. So let me write it. So the Schrodinger equation I can write like this here, you see, and this I am writing for an anucleon system where the nucleons are interacting with each other. So nucleons interacting with each other through two-body interaction nu. Okay. Now I have introduced a mean field ux. Let us now introduce this. So let us now introduce mean field ux, and as a result I will write the same Schrodinger equation, now a little bit different, you see, here, like this. I am writing the same Schrodinger equation, but here I have introduced the mean field. And V is basically the residual interaction. Okay, where you see the H0 is minus h square del square by twice minus 1 plus u. This is basically the unperturbed single particle Hamiltonian of the shell model. That is the which uses the harmonic oscillator potential u. Now we already have learned that residual interaction actually it plays a very important role. You see the energy levels which I just talked about previously in 18 oxygen, you remember? So 18 oxygen and 10 neutrons and 8 protons. Now so you can think of it as 16 oxygen 8 plus 2 neutrons, and they were in 1d 5/2. Now if you do the angular momentum, so you get J is equal to 0, 2, 4, right? So we can have 3 states, 0 plus, 2 plus, 4 plus. Now in absence of residual interaction, the 0 plus, 2 plus, 4 plus states are degenerate. They are the same energy. But experimentally, we observe 0 plus, 2 plus, 4 plus different energies. So this means that basically they tell us about the presence of residual interaction. So it is basically the residual interaction which is not causing them to be degenerate. Okay. So let us now consider the residual interaction. So let us consider the residual interaction between two nucleons given by this term. Like this. Now using the perturbation theory, it can be shown that the energy, so using perturbation, let me write it in the next page. So using perturbation, I am just writing the result. You don't have to do the calculations. It is very big. So just I am writing the results. The result is very important here. Now using perturbation, it can be shown that the energy of the two nucleon system, where each of the single particle levels, so two nucleon system, single particle levels are N alpha, L alpha, J alpha, and N beta, L beta, and J beta is occupied by one nucleon, each of these single particle levels, and their angular momentum coupled to total angular momentum J, it changes by an amount so basically the energy of two nucleon system, the details are here, changes by this amount as a result of this pairing interaction, as a result of this interaction form which I have assumed over here, a delta type interaction, due to delta type interaction. Residual interaction. But this is not all. The other details, what is F and all that, let me write it down. So here F is this, and this A is also a very big number, this A. Again, you don't have to write this, I will tell you. Now here you see this UNR, NR is the radial wave function that we have defined previously, harmonic oscillator case, right? Now you see these equations over here show that the energy shift by the residual interaction depends on the total angular momentum J. So moral of story, what's the moral? The moral is that energy shift delta E by residual interaction depends on spin J only through a factor A via this factor A, which involves the Slave-Jordan coefficients and 2J plus 1. So CG coefficients involved in this. Now in fact it can be shown that if we show this table as a function of A, it is very interesting. But anyway, I will not show you the results over here, but rather discuss the importance. আমি যদি সিজিটাকে plot করি আর here you see what I have shown you is the J dependence of energy shift factor A, and this is shown for J alpha is equal to J beta is equal to 9/2. So basically what I am showing you is that what happens when we fill two identical nucleons in the same G9, say 9.5 orbit. So what this table suggests, what does it suggest? You see, what it suggests is basically the energy splitting among the 0 plus, 2 plus, 8 plus, which has been induced by the short range residual interaction of the delta function type. So you see what I have done till now, basically you can use this to explain 18 oxygen, but it will be better if I talk about this 210 lead here. So here previously I talked about 209 lead, remember. Now I am talking about 210 lead. So here we have got two neutrons in the G9.5, and you just remember our previous argument using the M scheme also I have shown you that for two identical either neutrons or protons, we will only have even values of the spin. So we will expect for these two neutrons in G9.5 0, 2, 4, 6, 8, maximum up to 2J plus 1, so up to 8 only. But see the experimental spectrum, these spins, the states 0, 2, 4, 6, 8, they are not degenerate, they are different in energies, and this is caused by the residual interaction. And right now what we are doing is basically we are trying to actually find the source of this residual interaction, and the simplest possibility jeta amra ekhon use korchi, we are investigating, is the delta type residual interaction. Okay, so right, previously I showed you this table, okay, and this table suggests that the energy splitting 0, 2, 4, this is what you expect from the residual interaction. এবার দেখো মজাটা দেখো, এইখানে যেটা দেখতে পাচ্ছ সেটা হচ্ছে the J is equal to 0 state appears as the lowest energy level. Why? Here also you see J is equal to 0 state appears in the lowest energy level, because you see in this state two nucleons move in the same orbit with opposite spin. J is equal to 0 means opposite spin move korbe in the same orbit, like this, in the same orbit, and so that the spatial overlap is large. As a result, your spatial overlap is large, and that's why you see they have the lowest energy. Consequently, the correlation energy is very much attractive for the and the delta function type is maximized over here. Now the spatial overlap of the two nucleons gets smaller with increasing J. Why? What happens? With increasing J, the different orbits, so this gets changed, the angle between them changed. For J is equal to 0, it is maximum overlap. J is equal to 2, it's like this. J is equal to 4, it's like this, and so on and so forth. And you see the overlap decreases, and as a result the correlation energy also decreases, and so accordingly you see the energy shift from the energy in the independent particle model becomes smaller. Remember আমরা কিন্তু shift calculate করছি. You see this expression, I am calculating the shift as a result of including the residual interaction, shift in the energy calculated by the independent particle model. Okay, so note this. Now note that the energy shift for the J is equal to state is especially large. দেখো এদের সাথে comparison করলে এই shiftটা অনেক বেশি large. So let us do this explanation. The energy shift for J is equal to 0 state is spatially large, and the interval and that the interval between successive energy levels gets narrower with increasing J. দেখো এই ছবিটা, look over here, this gets narrower with increasing values of J. Now this J dependence, which I have shown previously in this figure over here, this J dependence can be understood by following an asymptotic formula which holds for J and capital J large. And what's the formula? Let me write it down. The formula itself. The formula is this. Oh, just a second. So this is the formula. You see, it depends on 1 minus capital J by twice J whole square. So you see, in the ground state of the nuclei, two identical nucleons occupy two orbits, which are time reversed orbits to each other. As such, of the total angular momentum J is equal to 0. You see, this is maximum when J is equal to 0. Okay, and this is known as pairing correlation. So, pairing correlation in nuclei, and this corresponds to Cooper pair and superfluidity in condensed matter physics. So this is what I have to say. This is important. You remember that this thing is maximum for J is equal to 0, and it decreases slowly. No, not slowly, quite fastly, with increasing J. And this is the reason for this. So two things we can explain. Energy shift for J is equal to 0 is especially low or very large, and the energy between the successive levels get narrower. So these things we can explain using this asymptotic formula. So that's it for today. Any questions you can ask? Let me say, so basically বলো না, এক মিনিট আমি একটা কথা বলে দিই. So today you see, before I finish, so we have talked about what is doubly closed shell nucleus. After that we talked about doubly closed shell nucleus plus minus one nucleon, either proton or neutron. Then এই যে last example যেটা আমরা দেখছি here right now, we have talked about plus two nucleons, so two proton or two neutron. And here we have talked about the delta type residual interaction or pairing correlation. So this is what we have done today regarding the doubly closed shell nucleus. And previous to that, we talked about how J is equal to 0 for core. You can understand from quantum mechanics and also the M scheme. So that's what we have discussed. হ্যাঁ বলো.